Hey guys, welcome back. It's been a while. So basically, I've been mostly shifting my focus in terms of real life stuff in towards applying for software positions and just trying to work on like portfolio projects and just dealing with stuff in real life. So I apologize that this channel has sort of just like fallen off, but I do intend to on occasion upload like a gaming video or like a programming video like you're watching now. But that's enough of real life stuff. So, speaking of those portfolio projects, one of them that I've been working on, I've been trying, well, for a while. If you've been following my channel, you'll know that I've been working on my own sort of programming language. For a while, it was called C, and then it transitioned into Zenith. And Zenith is still something I'd like to work on in the future, but I just have to be realistic and understand that I can't really just do that right now. It's going to just take too long to get it exactly where I want it. So instead, what I've done is, in order to demonstrate that I have those sorts of skills, right, I've created a fake assembly language called Topasm, the obviously practical assembly language. And so in this video, I just want to sort of demonstrate some of its current capabilities and talk about where I want it to end up going. So if you've been watching my previous videos, you'll notice I've changed some of my terminal stuff. So I'm using tmux now, and I'm using nvchad for NeoVim, if you're interested. If you want to know more specifics, you can ask me. I can like share part of my config. But anyway, I guess the first thing I should do is probably just open up Vim. So you'll notice I've written this in Go because I figured if I'm going to write another Lexer again, I may as well also learn a new language. So I've decided to learn Go because I didn't know it, and it's a pretty reasonable language. All in all, after having been working in it to the point where I'm like very reasonably comfortable, I mean, I'm like comfortable in it at this point. It's like pretty solid, but there's just some decisions I really just hate in it. But for the most part, I think it's a really nice language. So we could just take a look at our main.go. It's really simple. It's just whether you speak Go or not, it doesn't really matter. Basically, we're just taking command line arguments, and all we want is to pass in a file name. And if there isn't one, we just do a log.fatal and end the program, etc. We can then parse the file path. We can then build a list of tokens. We can then build a tree. And in this case, I'm interpreting because I've always really wanted to learn assembly, but I've always found it's like a really big pain. So if I open up a different tmux session right now, and go over here. No, I opened VI, I think. I'm also using a new keyboard, so this is kind of like a pain. I'm still sort of learning it. I'm using like Dvorak, and it's really interesting stuff. Yeah, I should just alias VI to Vim, honestly, because I'm never going to use VI. But, like, here's a very simple C program, right? We have two numbers, and we're returning their mod. And then you look at the assembly, and you're like, oh my goodness, how am I supposed to understand what's going on? And to be honest, most of this stuff isn't actually useful for us. Like, the only useful stuff here is sort of in this section, in the main section, where you can see, for example, the idivl call, and like move long and pop and stuff. And like, I want to be able to write something like this, but this itself is clearly too complex. This was compiled by GCC. I guess something else I could try is if I just use Clang instead. That's where my tab is. Okay, main.c, and then I imagine it's also just like -s. I feel so slow. But yeah, now this you see is completely different than what we just had. There's still like a lot of confusing stuff here. Like I have no idea what these offsets mean or anything. And one of the annoying things I find about assembly is the two different styles. In one of the assembly styles, you have like, we're moving 0 into this register, and in the other one, it's like, well, not register, memory address. But in the other, it's like reversed, which argument comes first. I've always found that sort of challenging. So basically what I've decided is, what if we just had a fake language that you could write assembly code in, but it doesn't actually like produce binaries that run on one CPU architecture? What if it's just interpreted so it can run on like any system? And it doesn't have to be performant, because the point isn't to write programs with it. The point is to learn the control flow of assembly, because this is a very different programming experience than writing like C or C-like languages, any sort of procedural high-level structured languages where you have things like loops and functions and all those control flow constructs, whereas here we basically just have like jumps and labels. And it's technically functions, but anyway. If I now go back to Topasm, what would be the best sort of way? I mean, I don't have to walk through all this code. One thing I might consider is doing a tutorial on how you actually can build this for yourself, because it is relatively simple. I guess I should look at sort of my context for the interpreters. So the question is, what sort of system am I simulating here, right? I represents just the like place in the tree that we are, like which instruction we're on. I use that so that I can then jump around using, jump commands. But here's the sort of the meat of everything here. I've decided to have in my system, my fake system, we simply have 10 registers, and they are written as #0 up to #9, basically. And all of them represent an unsigned 64-bit integer. And that keeps everything simple, because all we have to deal with is 64-bit integers with no sign. Every value in Topasm is that. And we also have 2 flags, which I can sort of get into later, but basically there's just an equals flag when you do a comparison and like a less than flag. And of course I have to store all the labels, but this code isn't too important. Let's actually just get into looking at an example. And I think for this case, it's probably best I just write one from scratch. So I'm not sure precisely what I actually want this example to do, but I can just call this, I'll just rename it later. So I'll just say YouTube example.tasm, Topasm. And let me close this. Okay, so just to demonstrate sort of what this is doing, because of course we have multiple commands. It's very limited, this instruction set, because of course this is a very simplified assembly. But first things first, you can write comments using semicolons. Anything after this is a comment. New lines are significant, so you don't need like a semicolon to end a line. You just need to keep one instruction per line. So to begin, let's just do something really simple. Let's move the number. Let's move the. Oh goodness, this keyboard setup. Let's move the number 10 into register 0. So you see, because I was really annoyed with like figuring out which way is the value moving, which side's the register, I just decided to add predicates basically in between. Sort of, it makes it more readable, I think. And it's like, again, this isn't meant to be like you're writing this for a job because you're trying to make a real program. This is just like for educational purposes, and yet it's still functional. So we're moving the value 10 into register 0. And then what we can do, I feel like I should have gone over the other sort of commands first, but basically you have what we can do now is we can use the call command or instruction, and we can call built-in functions using call. And I currently have 2 built-in functions. There's print I and print C. Print I will simply print whatever is in register 0 as an integer. It just prints the integer value of register 0. Print C will print the character in register 0 based on ASCII value. And right now, the only way that I have to print characters is by using the ASCII code. Soon I'm going to parse like character literals, and I'd like to parse string literals. I don't currently have a stack or any sort of memory. It's all just registers, but this is very simple, right? We're moving 10 into register 0, and then we're calling print I. And so I can come into my terminal, and I can then run, I can do go run dot, and I can give it the file as the argument. In this case, it's YouTube example.tasm. We run it, we get 10, and you see the % sign there highlighted means we didn't actually print a new line character. But what we can do is, turns out the ASCII value of a new line character is 10. At least, in Linux with LF, you don't need a carriage return character first. So what we can do is we can call print C, which will then print the character value of register 0, and we already have 10 in register 0. So if we just add another call afterwards, we then print the value 10 followed by a new line, and it works. So now let's do something a bit more interesting. In fact, let me just go through my README, because I did sort of spend time to actually write out the commands. Instructions. I'm going to keep saying commands. So we have move, like you've seen. You can move a value into a register. There's obviously addition. You can add a value into a register. And notice I say value. When I say value, that could be an integer literal, like we've seen in the previous example. If I undo all that. This is an integer literal. It's a value. But suppose we had something in register 9. We could also move that into 0, because a register also has a value, and it can read it. In our case, every single register will start with 0. So if I did that, it wouldn't actually matter. But anyway, of course, you can sub. You sub a value from a register, so you're removing it. And of course, we have an increment and decrement. I decrement the value by 2. That's not right. Okay. It's always fun finding things that you messed up for. So those are the very simple instructions. And in the future, I'm going to add more things like left shift, right shift, like bitwise and, etc. Things like that. I might also have like a print binary. There's a lot I can do with this language, but I have it in a very simple place where it's like surprisingly functional for how minimal it is. Then we have some advanced instructions, right? And I've tried to mimic the like x86 instructions sort of the best that I can with my very limited understanding, which is why I have this open up over here so that I can actually just take a look at real assembly code. But so it seems that multiplication and division are different from the other operations. I could have made it like you multiply value into a register, but that isn't how these work in x86 as far as I understand. The way it works is it actually just takes a register, and what it does is it will multiply the value of the 0 register, in our case. I think it's EAX in x86. But we're going to be multiplying the value that is stored in hash 0 by whatever is in this register, and then the result will be stored in hash 0, that's okay. And then you get division, which is a little bit more complex. Again, you'll notice that since everything here is an unsigned integer, I don't need like divq or any sort of size reference, because everything is 64-bit. All of these operations are just 64-bit, for better or for worse, just to keep things very simple. Now, divides works pretty similarly. It will divide the value that is in the 0 register by the value in this register that you pass in as an argument. The quotient, so the result, will be stored in the 0 register, but the remainder will then be stored in the number 1 register, because that's basically how division works in assembly. You don't have like a remainder instruction. It's just you get it as part of the output of division. And then we have the compare instruction, which is actually super useful. So you can compare a value with another value. And I've done it this way so that you don't necessarily need things to be in registers. It's hard for me sometimes to know when I should use a value and when I should use a register, because it doesn't really matter, right? Like, I'd like to avoid integer literals for some things, like obviously, like when it comes to division multiplication. But anyway, what it's going to do is it's going to compare the first value against the second value. I've called them A and B. And simply, internally, we're setting some flags after this comparison. We're setting the equals flag. We're setting it to true if A is B, and we're setting the less than flag if A is less than B. It's that simple. And these will always remain constant until you do another comparison call. They will keep their state forever until you do another comparison. That's currently how I have it. Of course, you can create labels. In my case, it's just an identifier followed by a colon. And an identifier is just uppercase letters, lowercase letters, and underscores. That's it. So you can just mark a place in code to jump to. So I guess I can demonstrate that pretty simply. If I, again, let me move, I guess I didn't, this will be faster. So we'll move 10 into 0. And then what I can do is come down here and say, I'll create a label called skip. And we're just skipping, but after skip, we're going to basically just print the value at, I have to call. Previously, I had print I be its own instruction, but of course that isn't particularly realistic. So I'd rather at least do some sort of fake call thing. Because again, as an educational tool, what this is showcasing is that you can call functions and they have a certain calling convention where they expect arguments to be in certain registers when you call them. So we can call print I, and then in case it's not 10 in there, we can then move 10 into the 0 register and then call print C. I'm going to separate this out just so it seems a bit different. And what I can do is, let's do something a bit more complicated now. We can, well, I guess I just want to demonstrate a non-conditional jump first. So we can just simply jump, oh, I did this wrong. I need it to be more like this. So I want to just jump to skip, for example. And this should basically just do what you expect, right? We're moving the value 10 into the 0 register. We're then jumping to skip unconditionally. If we didn't jump, we would call print I, which would print the value 10. But after skip, we will then, move 10 into the 0 register, which is kind of redundant here. And then we'll call print C to get a new line character. So if I run this, did I save this? Jump, skip. It'd be lovely if this isn't working right now. Move 10 into 0. Jump to oh boy. Am I going to have to actually look in the... Because if I go into my interpreter, let's just take a peek. This video is horribly unstructured, by the way, but, maybe it's interesting. Oh, why is there nothing here? Oh, well, there's your problem. Oh, right, because yep, okay, I see what I did wrong. I just need to do an unconditional jump. So now, it was essentially a no-op, but now it correctly unconditionally jumps. And we don't do this call because we're jumping, because that's just how control flow works with assembly. And so you'll see I have a handful of jumps that are useful. There's the non-conditional jump we just saw where it doesn't matter, we just jump. Then there's a jump not equals. I've opted to use capital letters to sort of make it a bit more readable here. So we can jump to... So jump not equals it simply checks if the equals flag is not set. And if it is not set, we jump. The equals flag, we just check, or jump equals, we simply jump if the equals flag is set. Less than, we jump if the less than flag is set. And now the next few will be a little bit different because, for example, greater than. Well, when do you know it's greater than? Well, it's greater than if it's not less than and it's not equal to. And so we have to check both of those flags and then jump. Less than or equal to? Well, that's simple, right? We jump if it's less than or if it's equal to. And the greater than or equal to, well, it's greater than or equal to if it's not less than. Like, it's basically just Boolean logic. But using these jumps, we can then have things like if statements or while loops or whatever we want. And then, of course, there's the call instruction, which calls print C and print I. And that currently is literally all of the ability of this language. This is all it can do. There's literally nothing else. And yet, even with this very limited instruction set, we can do like a surprisingly large amount of things. So for example, in this one, let me get rid of this line, I've implemented the printing of a lot of Fibonacci numbers up to 610. So let's sort of just walk through this to sort of demonstrate what's happening here. So I'm initializing our values. I'm moving 0 into 7. I'm using the registers near the end because for a lot of these commands, for a lot of these instructions, they use like the 0 or 1 or 2 register. So I'm trying to just store my values in the further ones so that I don't have to really move them ever, just to keep them preserved between function calls and things. I don't have to move 0 into 7. I'm just doing it so that it's clear for the code, like which value is what. I'm starting with 0 and 1, where 7 represents the last one and 8 represents the current. And then we can just make a label and make a loop. And then what we can do is we can print the current value, which is represented by the 8th register. And how do we do that? Well, we have to move that value into the 0 register and then call print I, which will then print the number. Initially, it's going to print 1. And then we can move 10 into 0 and call print C to get a new line, which is something you're going to see all the time. And then what we want to do is we want to do the normal sort of Fibonacci thing where we set the last to current and we set the current equal to current plus last without like losing the value, because this sort of thing, you'll realize you need a temp value anytime you do something like this. So I'm simply storing the current value into register 6. I'm then calling add to add 7 into 8. And then I'm moving 6 into 7 to get the temp value back to the previous. And then what we do is we'll compare the current value with 610, which it's just one of the Fibonacci numbers, because I just wanted to go like up to a reasonable point. So, and I want to test my less than or equal to. So I said, let's go up to 610 and we will jump if less than or equal, we will jump to loop. And so internally, this is going to handle all of that by setting flags and things, which is sort of, from what I understand, basically what a CPU does, is it will set flags when you do a compare, and then jumps will sort of do that. And so you can see, even though this is a very simple language, and it's non-performant, and it's like basic as heck, you can see how much like assembly concept somebody could learn through this language by just playing around and seeing how this control flow works. Now, of course, let me actually showcase if that works, because if it didn't, is it capital F, lowercase? Right, print Fibonacci. And you see, it does 1, 1, 2, 3, 5, etc. up to 610, because that's when we said to stop, and it will print all those Fibonacci numbers. And of course, we could change this. If I go over here, I could change this to be, I don't know, let's just add some zeros and then see what happens. And there we go, we get more Fibonacci numbers. Because, and you saw, like, even though this is an interpreted thing, it is basically instantaneous for what we're using it for. I wouldn't recommend writing a server backend in Topasm, but hypothetically, if I add enough commands, you could, which is kind of cool, in all honesty. I wonder if I'll get to the point where I could write an interpreter for Topasm in Topasm, but that would be awful, because then you'd have 2 layers of interpreter. And then what I could do is I could write an interpreter in Python, so it's 3 levels of interpreter going on. And it will still be faster than JavaScript. Okay, so this is pretty good. I really like this. If you guys are like interested in this language, you can check it out on GitHub. I'll have a link in the description. I'm going to add, let's talk about now what I plan on in the future, because obviously this is very limited. I think the big thing that's annoying me right now is having to look up ASCII tables to print out characters. I really want to make this syntax actually work. So I'm going to add characters to the language. The way it's going to work is essentially just, obviously in terms of parsing, it's pretty simple, but in terms of like what it's going to do is it's simply going to be like an integer literal, right? You have a character literal, it's just going to be replaced with its ASCII value. And so you could just use this, you could like move a new line into 0, and then if you said print I, it would just print 10. But of course, calling print C, you'll print the new line, which is exactly as you expect. So characters will be very easy to add, I think. That's not too bad. The hard part is going to be adding strings, because one thing I haven't really mimicked that is a very important concept in assembly is that when you're writing assembly, like the file itself sort of matters in the sense of like if I put a string up here in this file, then in the binary file, the string will be here in the file. Like, if you sort of know what I'm talking about, I don't know how familiar you are with assembly. Let me change this real fast so that I actually have a string. and let's do a printf, and let's just say, it literally does not matter what we say. So let me just do this, and we'll just return 0. Come over here, compile with Clang because it doesn't really matter. And what you see here is at the top, or actually, supposing Clang, it's actually down here. You see we have this label of whatever this kind of label is, I have no idea. But it says string, and we have some ASCII thing here, and you see the string literal is here. When this assembly file is actually going to be produced into binary, I'm sure I could. There's definitely commands that would allow me to see it, but I'm not proficient at them, so I'm not going to bother wasting your time on it. This is going to actually be in the binary file, basically. It's going to place S as a number, followed by T, followed by the whole thing in the file as part of the code. And then every time you want to reference this thing, you reference that memory address. That's how strings basically work. And then, of course, it's null terminated. At least I'm assuming that strings in assembly would be null terminated, because why else would they really bother in C to null terminate them? But so you see, for example, here, right here, we're calling I forget what LEA stands for, but we're doing something to this string, and RDI, I forget which register that is. That's kind of an important one, I think. So I know that this is like the stack pointer. RDI, I don't remember. But then you see we're moving something into the low half of A, the A register or whatever, and then we're calling printf. Sort of like, this is sort of what I'm mimicking with my language here. Is like you see call printf, and there's just things in registers. So what I'll really have to do, we go back now, there's like two sorts of big steps that I need to take with my language first, and that is introducing the stack, because as you'll notice, I only have 10 registers to hold values. I do not have access to memory. I only have the registers built into the CPU. So what I'll probably do soon is sort of try and mimic having like a stack pointer and having memory in that in some way. Of course, it's all going to be unsigned integers, and I'm not exactly sure how I'm going to manage that yet. But that would be a next big step to make this more legitimate, is actually having that. Another thing I could do after that is maybe add like a malloc function or something so that you can actually have heap memory as well. And I could even add like data stuff, but I also don't want this to be too complex, right? Because as fun as those features are, keeping it nice and simple is really cool. So I'm going to add a little bit more depth to try and make it a bit more realistic, but I don't want to like spend another 3 weeks just making it a real assembly language, because this isn't the point. This is supposed to be Scratch for like assembly, right? This is supposed to be, you pick this up and you're like, oh, I kind of see how assembly works. And then maybe you can delve into like a book about x86 or ARM or whatever. Now, there is one big thing I do want to work on. Since I use this as an opportunity to learn Go, I'd also like to use it as an opportunity to learn web development using Go and HTMX. So what I'd like to do is make a website that anybody on the internet can go to that has like a text box, and what they can do is they can enter Topasm, and then it will use this interpreter to produce a result. And the cool thing about a website is I can add, one thing I'd really love to add to the website is I can show you the values in all the registers and the flags, and then what you can do is I can have a walk through the code button so that you can go through the code on each instruction, and it can show you how the registers are updating and how the flags are updating. And then it can actually just show you the control flow and the result, which I think is going to be incredibly cool. It's going to be super useful in terms of like actually using the language. It's always nice, because it's really annoying when you find a really cool project on GitHub or whatever, and it's like, okay, I guess I just have to git clone this and build it myself. With Go, it's not too bad. I don't think you could just install Go and then clone my repository, and then it would probably work. But wouldn't it be nice if you could just visit the website in the description, which hopefully I'll remember to add if I ever actually get it working. But also in terms of Because what's the point of this, right? Other than the education, other than me learning Go, which I've done pretty well, like well enough. I would not call myself amazing at Go, but I can clearly use it to make something functional. Other than teaching myself Go and creating an educational tool for me and for other people to learn assembly, having that website as well, like, I think this just is a fantastic portfolio project for me to just demonstrate sort of like, look, I can just pick this up out of nowhere. I can just take a language I've never used and I can build a fake assembly language in it, plus a website that anybody can interact with. I think that's a pretty good demonstration of skills and a pretty good way for me to expand my skills. So hopefully this video, like a lot of these, isn't too just like all over the place nonsense, hard to follow kind of deals. But yeah, if you're interested in my like terminal setup or whatever, you can feel free to leave a comment. If you're interested in my keyboard setup, that's actually a more interesting one that I might want to just make a quick video on just to share because it's cool. In my opinion, it's cool. It's really interesting. I have an Ergodox Easy, if that gets you more interested. And oh yeah, if you're interested in actually learning how to create an interpreter for this language, let me know and I could do a quick series on it, because the good thing is, unlike previous series that I've unfortunately had to just leave because I haven't been able to make progress, this one's already done. You can actually see it is functional, at least to some extent, right? It is functional, which means I could actually then make a series to showcase this. And just quickly, I suppose I can go through some of these files to show what I have. We have like token kinds, which is sort of like we're representing the types of tokens that we have. We then have some methods. This is just how you do it in Go. Our tokens just have a type, the string, and like which line of the file they came from. My error handling's not really the best. It's very sort of minimal, but that has helped me make this a lot faster. So for example, if I instead say move 10 into 0, and I run this, that's the wrong file that I'm running. Pressing up, even though it doesn't look like it. No? No. You see error expecting one of hash on line 1, which, that's interesting. Why? Oh yeah, because it's the parsing, right? Because basically it's the parser saying we expect a register here, which means we need the hash symbol. And it's not like the best error, right? It's like, well, you mean one of these symbols on line 1, but this doesn't need like a good built fault handling system because it is very simple, and I didn't want to be bogged down trying to handle faults in a very functional way where every function has the possibility of returning. I'm just like, no, I'm just panic, just print the value and leave. It makes the code so much simpler. And again, this is not meant to be like a development tool. This is just meant to be like a quick play around and find out. And in the future, I can always go back and improve the fault handling. But yeah, like this is it. This is the whole token file. Like, this is it. It's just a handful of like one-line methods. Like, it's not complicated. If we look at our Lexer, well, let's see. We're making tokens, and that's it. Like, it is so small. It is so little compared to the ones we've had in previous series in the past. Our grammar is this. That's it. We have these handful of symbols, we have keys, and we have specifically jump keywords. Source file, I've sort of built a similar thing if you've seen previously. It's a bit more complicated, but it's really handy. Anyway, I think that's probably been enough rambling for today. Again, just let me know if you're interested in any of this stuff. Hope you guys enjoyed. See you in the next video.